Hey, good morning, everyone. Uh, it seems like your previous class just got over. Everybody just joined in. Okay, yeah, welcome to session number 7 of our course on network fundamentals for cloud. So last time, actually yesterday, we completed the entire content that we wanted to cover around network fundamental topics. And this was essential because all that we've learned in the last 6 classes around the networking fundamentals. They are not just true for the internet, but a lot of those principles and concepts we will apply in data center networking as well. And also when we talk about virtualized networks in the context of the cloud. So while we had titled that module networking fundamentals, these are general fundamentals of networking which are applicable everywhere, and that is why we covered them in sufficient detail so that we have the basic knowledge to be able to understand the more complicated concepts arising in the data center. So with that done, from today we will actually talk about enabling technologies for data center networks and for cloud virtual networks. Okay, so we'll talk about the building blocks, and then in the subsequent class, the next class, we will start with the topic of data center networking. So let me just pull out my slide. I'm already sharing my screen, and our class is already being recorded. So just put it on slideshow view. Okay, so we will start with the topic of software-defined networking first, then go to the topic of network virtualization and also network function virtualization. So we'll cover both these topics. What is network virtualization and what do we mean by network function virtualization? Okay? And once we've done that, then towards the end of today's class, we'll try to tie up these two together and see how software-defined networking and network function virtualization get applied together in the context of a data center. Okay, so while both of them are independent technologies in themselves, and while both SDN and NFV can be applied in isolation, I mean, they don't have to be tied up together. SDN is a technology in its own, can be used in any network, generally under control of a signal network administrator, but also in a group of collaborating networks, the concept of software-defined networking can be applied. Network virtualization and network function virtualization, on the other hand, is a separate concept altogether. It's an independent technology. But the reason why a lot of times the term SDN / NFV is used is because the two of them, SDN as a technology and NFV as a technology, are used in tandem together in the context of the data center networks. Okay, so that's what we will look at towards the end. But first, we will try to individually understand each technology. So, couple of classes back, actually 3 classes back, we started the topic of network layer, and we distinguished between what is the data plane functions in a network layer and what are the control plane functions of a network layer. And we had said in the data plane, there's a local function that every router implements in the data plane, and that is the function of packet forwarding. So when a datagram arrives on an incoming port of a router, the router looks up a forwarding table, matches the uh, most likely the destination IP address in the packet header with the forwarding table, and then it uses it to forward the traffic to the output port. So this is what's happening in the data plane. The actual handling of data happens in the data plane. But to enable this function of the data plane, the network layer control plane implements a network-wide logic, which is determining the route that the datagrams should be taking from the source to the destination. And once the entire route is identified, then the forwarding tables are accordingly populated for the data plane to make that local decision of forwarding. So when we talked about the control plane, we had also mentioned that there are 2 approaches to implementing the control plane. One is the use of traditional routing algorithm, which is implemented in almost all routers that exist across the globe, and what is predominantly the technique followed in the internet. But I had also mentioned that there is a technique, separate control plane implementation technique that revolves around using software-defined networking. And this is often used in some special kind of networks which have specific requirements. So we will talk about what those specific requirements are, and the example that our course will take where SDN is very much applicable is the data center network. For now, let's suffice to say that generally for software-defined networking to be implemented, it's preferred to have a single administrative control for the network. So think of it like an autonomous system within which I can implement software-defined networking. A data center network belongs to a particular service provider, and therefore it belongs to a particular and single autonomous system. Software-defined networking can be applied over there. But why should we prefer software-defined networking in such cases like the data center network over traditional routing algorithms? That's something we will talk about right now. Okay. So recollect again that when we talked about per router control plane, this was our diagram. This is how it looked like. We had multiple routers in the network, and every router had a data plane function, which is a local function, which is the local forwarding action. But they all had an instance of the routing algorithm which was implemented. And this could be, as we discussed, link state routing algorithm, distance vector routing algorithm. And in the case of inter-autonomous system, we saw that this is the path vector routing algorithm, that is BGP. Um, Collectively, these routers interact with each other as part of their control plane function, determine the route, and populate their forwarding tables. We say that the routing algorithm is a distributed routing algorithm in this approach, and the algorithm is designed in such a fashion that eventually the routers converge on a route. Right? While they are working out, while they are discussing amongst each other, they are interacting, trying to identify the route. Eventually, the algorithm is such that it converges. For every pair of source and destination, it converges on a particular route, and that is what determines the forwarding table. The other approach to implementing the control plane is to, instead of having a distributed approach for route computation, make the routing computation approach centralized in nature. Okay? Now, this is very similar to how, if we once again go back to our Google Maps example and routing over a road network, the way the Google Maps algorithm would be working is it would be a centralized implementation in Google's own server machines. The source and the destination is fed by a subscriber of Google Maps to the server. The server centrally, having a view of the entire road network topology, provides the route to be taken by the traffic. So it's more of centrally identified and computed route. Same way in software-defined networking, we follow a similar approach. So we have what we call as a remote controller node. Okay? And this remote controller can be seen as a centralized entity which computes the routes between every pair of source and destination in a network. And then once that route has been computed, it goes ahead, computes the forwarding table for all the routers in the network, and then pushes them into each of those networks. Okay, so all routes are centrally computed by the remote controller, and then the forwarding tables are created out of those computed routes, once again at the remote controller, and then these forwarding tables are pushed to the data plane of every router in the network. Now, if you look at this approach, it is obvious that an approach like this, which is centralized in nature, cannot once again scale to a very, very large network topology, definitely not at the scale of the internet. So that is one of the reasons why I said that it's a preferred technology within an autonomous system or within a group of collaborating autonomous systems which agree on certain principles to apply a centralized control plane implementation. So this primarily is the difference between traditional routing and software-defined networking. The fact that the control plane function no longer exists in each of the router's network layer. Okay, so we earlier said the network layer in every router has a control plane and a data plane. Now we are saying the control plane function of every router and in the network layer is extracted out and moved to a central node. So every router, the network layer now only has what we call as the data plane. So this is primarily what SDNs in a nutshell is all about. But to understand why this came about, we'll have to try to understand a little bit of the history of networking. What was the architecture for traditional switches and routers in a network? How did these switches evolve, and the architecture of these switches evolved alongside? Why did the concept of control planes even come in? And why are we moving to a technology like SDN, which is kind of going retrospective, a step backwards, as we will see the journey of how switch architectures have evolved? Because we want to meet the needs of special kinds of networks like the modern data centers. Okay, so if you have to understand the evolution of switches and primarily the control plane functions within these switches, then we'll have to start from how the traditional switch architecture looked like. And in a actually class before, when I introduced the control plane, we had briefly covered this. And at that point, I had said that if you look at any traditional switch, a switch typically has three planes. And these planes exist in every layer of the protocol stack. So when I say every layer, the layers are the TCP/IP protocol layers, application layer, the transport layer, which we covered yesterday, the network layer, the data link layer, and the physical layer. So these are the layers. Now, all we are saying now is that we are splitting these layers into three parts. We are saying every layer has three functions. One is the data plane function, one is the control plane function, and the third is the management plane function. So every layer implements three key functions. I mean, the functionality is logically distributed between data plane function, which is primarily handling data, packets, right? Reception of packets, transmission of packets, the implementation of the forwarding table. All of this is function of the data plane. So the data plane primarily does the packet buffering in a router. It does the packet scheduling, which packet should be picked up first. And this is specifically true when you have a quality of service based packet scheduling. So you have multiple queues, each queue having a different quality of service, a high priority queue, a medium priority queue, a low priority queue. So then packet scheduling has various algorithms weighted. The simplest is first come, first serve. But then there are a lot of other packet scheduling algorithms like weighted fair queuing. And all of them are done as part of the data plane. Plus, we also saw that when the packet is forwarded, some fields in the packet header may need to be modified. One of the things we looked at was the time to live field. We said that the time to live has always required to be decremented by 1 before forwarding. All these functions happen in the data plane. But the control plane is what enables the data plane by exchanging certain information with the data plane, which enables the data plane to go about doing these functions. And we looked at the primary function in the network layer being that of routing. This is the routing function that we talked of in the control plane. And then there is this management plane, which implements the network management protocols like SNMP, which configure and manage each of the layers of a traditional switch. So that is what these slides are talking about. I'll skip these. I mean, I've already given a gist of what these three planes are, and I've reiterated what they mean. Now, if you look at how switches and the control plane functions within these switches have evolved over years, then one of the things that we will find is that over years, we move towards a more software-driven approach. Hardware-driven approach. Okay. When I say that we move towards a more hardware-driven approach, it means that more and more functions of the control plane and the data plane have moved into chipsets that represent hardware more than software. Okay. So if you look at the 1990s, for example, the physical layer was primarily the layer which was implemented in hardware, whereas the rest of the functions, including data link layer forwarding, layer 2 forwarding, the function of network layer routing, any quality of service related packet forwarding, Implementation of access control list. Access control list is like a firewall. I mean, you determine what traffic is allowed to pass through and what is not. It's an access control list. All of this was largely implemented in software. Okay, so these functions were primarily in software because it's easy to manage, control a software. If there's a bug, you can patch the software very quickly. If there's a bug in the hardware, it takes much longer to fix it. Okay? One is longer. The second thing is cannot be remotely fixed, unlike a software update which can be done remotely. A software patch can be pushed remotely. So in 1990s, bulk of the functionality of the data plane and the control plane were implemented in software. But as the traffic rate grew, see, remember, 1990s was the beginning of what? It was the beginning of the internet. So the only people who were using internet were the larger enterprises which were connecting to each other and the rest of their branch offices, head office over this internet. But there was not a huge amount of traffic that the network was handling at that point in time. So this approach of having bulk of the functionality implemented in software, whereas some of it being in hardware, worked reasonably well. But as traffic grew from 1990 to 95, the internet started to become popular. So in 2000, more or less every home had an internet connection. 2005, when broadband became extremely popular, so everybody was talking about 2 Mbps plus of data rates. That's the definition of a broadband connection, anything over and above 2 megabits per second. As the internet became more and more adapted by people, the traffic over the internet grew. And as the traffic grew, we know where this pressure is going to come into. It's going to come into the data plane. Because the data plane, as we said, is the fast path. It has to operate at line rate. These are statements that we've been making in the past. And therefore, gradually, data plane functions started moving from software to hardware, primarily because of the speed that you could achieve implementing the same function in hardware. Okay, so customized ASICs, application-specific ICs, started to get built. If you needed more flexibility than what an ASIC could provide, then you would go with a field programmable gate array, so that you could actually program this FPGA in field and do some patching if required or changes if required. But if you're very finicky about flexibility and still want the functions to perform faster than the hardware chips that were brought in, was the concept of network processors came in. Okay, so these are processors like your general purpose CPU processors. These are special purpose processors focused towards implementing the networking function of the data plane. Okay. So we saw that layer 2 forwarding function got pushed into hardware. Some of the other functions like routing, implementation of access control lists, quality of service based packet forwarding. By 2005, we saw bulk of the data plane functions had already moved into hardware, and it was primarily the control plane, which we also call as the slow path because it doesn't have to work at the line rate. The control plane functions were the only functions which remained in software, which were implemented on your CPU as part of your operating system protocol stack. Okay? So this is how gradually the whole functionality of the data plane eventually moved from residing in software-based components to completely hardware-based components. Now, while this gives performance to a switch, when you move the data plane functions to ASICs and custom-built network processors, it improves the performance of the switch. What it also brings in is a level of rigidity in the implementation of the switch. It's not flexible enough to patch it. If you have a new protocol, I mean, the reason I'm saying this is the networking protocols have continued to grow. And the last bullet on the earlier slide, which I actually skipped because it's not too relevant right now, are case in point. I mean, these are techniques that came in over a period of time. So we'll talk about spanning tree protocol more when we come to data center networking, but it's a technique which tries to avoid any cyclic loops getting formed in the network, right? So that traffic doesn't keep on bouncing in a cyclic path within the network, never reaching their destination. So spanning tree protocol came in. It was enhanced with the rapid spanning tree protocol, RSTP. All I'm trying to give you is examples that the functions of the networking layer continue to grow with new and new protocols that keep coming in. And this requires alterations to the switch functionality, which cannot be so easily done if you implement all the networking functions in hardware. So while hardware solutions were leveraged to help the routers and bridges keep up with the increase in traffic and the increasing speeds of the incoming links and outgoing links as well, the communication links went from few hundreds of kilobits per second to terabytes, or at least at the very minimum, even the local links became gigabits per second. So that increase in speed required hardware-based solutions to leverage their performance and keep up with the increasing speed. But this led to reduced flexibility, and more often it basically meant the death of an original concept which was conceptualized, which was called programmable network. So programmable network is an old concept, but it revolves around the ideology that the networks themselves, including all network infrastructure and networking gear like your switches, routers, they should be programmable. I should be able to change the behavior of a network by simply making a software upgrade and controlling them via a programmable software-based interface. Okay? So this movement of functionality to hardware kind of felt a death knell into this whole ideology of having programmable networks, and networks became more and more rigid. Okay. But then came the world of the this whole space of cloud computing, where what evolved was a special form of networks that existed within a smaller geographical region, or you can call it an autonomous system, which was the modern data center. So what is a modern data center? As you can see on the right in a picture, a data center is actually, you can think of it like a warehouse containing a huge number of servers that are providing an immense amount of computational power to run a lot of services for the internet. Okay, so it's a warehouse, a powerhouse for running services that power the internet. Who owns these data centers? Some of the largest organizations and conglomerates in the world, they own these data centers, the likes of Amazon's and Microsoft and Google's. They own these data centers. But it's not just limited to the larger organizations, even enterprises which have a sizable, which are sizable in nature. Think of an organization like Oracle or Juniper, or even a services organization like a Capgemini or an Accenture. Okay? They have huge requirements for servers. Okay? Now, one is that they will deploy individual servers at all across the globe, but the other is they can set up their own private data centers or warehouse where you have what we call as rack servers. So what you see in these diagrams are racks. Right? And on these racks, you have blade servers which are put into every shelf of the rack. So pictorially, or if I diagrammatically try to represent the same picture as above, this is how it will look like. Each of these is a rack, and every shelf of that rack has a server machine, right? A blade server. Top of the rack, you have a switch, right? Which connects these servers not only to themselves, but also to the rest of the data center server. So we call it the TOR switch, the top of rack. TOR stands for top of rack. Right? So each of these has 10 to 12 different servers, and you have multiple such racks giving you thousands of servers in the same data center. Now, as data centers evolved, it led to the evolution of small, actually when I say small, I mean from a geographical spread standpoint, not from a compute standpoint, but it led to a small geographical autonomous system, which was small in its geographical spread, but had immense and huge volume in terms of the nodes that were getting connected inside of it. So there were thousands of these servers that were getting connected in a very small autonomous network inside of a data set. And not only was it limited to servers themselves, the concept of cloud computing, which we will talk about slightly later, where we will talk about the whole concept of virtualization. But I'm pretty sure that you are also doing this course of cloud computing in parallel to this course. So by now you've already been exposed to the concept of a virtual machine. Yes or no? Everybody understands you've been exposed in cloud computing to what a VM is, a virtual machine is. It's a virtualized instance of an isolated compute machine that exists on top of a hardware server, and there can be multiple such VMs running on a single server. So if I have 1,000 servers, let's say physical servers in a data center, and each physical server has the capability to run some 20, 30 VMs, then overall I'm talking about 20 to 30,000 compute machines in a single data center. Okay? Now, if that is the volume of nodes, each of these machines can be seen as a network node, right? They are connected to the data center network. Now, if you have 20, 30,000 machines connected via a data center network, and you're expecting the routers to be able to identify, using a distributed routing algorithm, the routes between each pair of these 20,000 server machines, so acting as source or destination of traffic. It will take an enormous time of a router's CPU to keep on looking at the network topology changes, rediscovering the new topology, recalculating the routes based on these network topologies. So even in a small size network, a regular network, as it exists in the internet, routers typically spend 30% of their overall CPU power in just doing this function control plane function of routing, in rediscovering network topologies, recalculating routes, and so on. Think of what would happen if the scale was to grow to the level of what we see in a data center network. Okay? The router are going to spend an enormous amount of time in just computing routing functions. Now, while that is one side of the picture, another very important thing to realize in a data center, which actually we will talk more in the next class, is that the nature of traffic within a data center varies very significantly compared to other autonomous systems that exist in the internet. In reality, for now, I will just limit to saying, next class I will talk a lot more about the different traffic pattern of a data center network. But for now, I'll just say that the changes in the network topology of a data center network are expected to be much reduced compared to that of the internet. The internet, as we saw, is a network of multiple networks. Each of them is an autonomous system in its own right. And therefore, every network administrator keeps on altering their network, changing their topology. Overall, the whole internet topology keeps on changing very, very frequently. But if you look at a data center network, once you've cabled the data center network and you set up the data center network, changes in the data center network topologies are rare and infrequent in nature. So having the distributed routing algorithm spend so much of their CPU computation power in rediscovering, recalculating routes in a network which is largely, I wouldn't say it's completely static, but it doesn't change so frequently, doesn't make a lot of sense. Now, this is only part of the picture. The real picture you will also see next class when I talk about how even the traffic pattern in a data center network is quite different, leading to different requirements for the control plane that we'll talk about next class. But overall, all these things meant that the traditional way of implementing distributed routing algorithms would not scale to the modern data center. And therefore, SDN came into existence. Okay, Jyoti says not able to see the screen. Everybody has that problem. I'm still on this slide. I've been on this slide for the last 5 minutes, the modern data center slide. Okay. Jyoti, it seems Rahul can see, so seems to be a local challenge. Can you try to check your network or maybe rejoin? Yeah. Okay. So some people can't, Priyank can't. Could be network challenge. I mean, as most of you can see, I think the challenge is not from my end. So you rejoined twice, Priyank. Okay. What do you see, Priyank or Jyoti? Is it no blank screen? Okay, it's visible for most. I don't think it makes sense for me to rejoin. So let's just try once more, Priyank and Jyoti. If it still doesn't work, then I'll make an attempt from my side. Okay. So SDN was designed to handle such unique kind of networks, which we call as the data center networks. Okay. Okay. What is Priyank saying? Blank screen is what you see. Okay. Okay, let me just quickly stop sharing and start sharing once more. Even though most of you can see, let me just, for the benefit of Priyank, and we stop sharing. Okay, so I've stopped sharing for everyone now, and I have restarted sharing. So just see if it works now. Okay, great. So it's visible for everybody now. Okay, I don't know. Maybe it's a Teams challenge more than a network issue at my end. I think it's more of a MS Teams issue. When you stop sharing, reshare, then it probably comes up. Right. So, but you were able to listen, and we haven't changed slides. So as long as you could get what I was saying, it's good enough. So STN was designed to take care of such unique kind of networks, which we call as the data center network, because data center networks have a traffic pattern, which is a shift from the traditional internet traffic patterns. Right? So, so SDN, as I said earlier in a nutshell, is an approach where I move the control plane function out of the routers and into a centralized node, which we also in the SDN architecture call as the SDN controller. Okay? So the data plane still exists, and the data plane exists in all these physical routers and switches, which we now call them as SDN enabled switches because they follow the SDN architecture, network architecture. So they implement the data plane. But if you look at the control plane function, it has moved out of these SDN enabled switches and it's actually moved into a central controller whom we call as the SDN controller. Now this SDN controller actually receives a lot of guidance in the form of business level networking requirements from various applications that are required to be implemented inside that SDN enabled network. Right? So if it's a data center network, then there are various applications, networking applications that you may want to implement in a data center network. For example, you might want to implement a network load balancing function as an application. You might want to implement a firewall as a networking application. Each of these applications, we call them being part of the application tier, and they have their own requirements based on which the controller decides how traffic should be forwarded or handled within the actual data plane tier of the network. So the SDN controller has two interfaces, one which we call as the northbound interface towards the networking applications, and the second which we call as the southbound interface towards the SDN enabled networking gear, which includes your routers and switches that exist in the network. Right now, you can ignore the figure which talks about virtual switches, but in reality, when we come to the concept of virtualization slightly later, we'll see that the concept of SDN doesn't just apply to physical switches. It even applies to what we will later define as virtualized switches or virtual switches. Right? Switches or switching functionality which is implemented in software. And so those we call as virtual switches. So SDN controller controls the data plane of all these SDN enabled physical as well as virtual switches, and that is the general architecture that of SDN. If I blow it up a little bit more to also show you what are the interface protocols that are used by the SDN controller to talk to the application layer and the data layer, you'll find that the applications typically talk to this control plane using standard API interfaces, most prominent of which is the REST-based interface. Everybody, I think, should be familiar with what we mean by REST APIs. So REST APIs are what primarily these application layer functions use to communicate with the control layer. These application layer functions, as I said, could be load balancing, routing, firewall, traffic shaping. So all forms of networking applications that I need to implement over a network. The requirements of those applications. This is how I want to route traffic. Load balancer says this is how you should be balancing the traffic across multiple equal paths in the network or multiple servers that exist in the network. The load balancer is giving its own requirements to the control plane layer. Firewall says this traffic you should allow to pass through, this traffic you shouldn't. All those requirements are coming via, let's say, the REST API to the control layer, which is the SDN controller. The SDN controller, knowing the network topology of the data center network or the underneath network, computes the forwarding tables. So it has the requirements coming from the application layer, it has the topology view of the network, and it computes the forwarding tables. It populates those forwarding tables using the southbound interface. The most commonly used protocol over the southbound interface is called the open flow protocol. And therefore, a lot of times, the SDN switches that you will find in market, they are also called open flow switches because of the fact that they support the open flow protocol. Okay? So we'll talk a little bit about what open flow is. It's an open source protocol used between the SDN controllers and the SDN enabled switches. It's the predominantly used protocol. Okay? There are other configuration and control protocols like netconf. SNMP can still be used to manage your SDN enabled switches. The entire forwarding table is populated as part of a database called the OVS-DB, especially for virtual switches. So OVS is a virtual switch, open virtual source switch. OVS-DB is the interface that is used with the virtual switch to configure the parameters and make the configurations in the OVS workflow. So there are a lot of different protocols that are used on the southbound interface, but the most predominant that you should remember is OpenFlow. So this is a three-tiered architecture that we call as the SDN architecture. Now, why is it SDN? Why that name software-defined networking? Okay. The term software-defined networking comes in because of the fact that in this architecture, I am able to take the requirements of the application layer. This is what the application layer wants from the network. It is able to specify it in software terms over a REST-based interface. And then I can take that requirement and implement it by setting the forwarding tables accordingly and populating them in the data plane of the SDN switches using the OpenFlow protocol. So in a way, I am implementing a programmable network. So if the application layer says, this is how I want the traffic to be forwarded in the network, I can take that requirement, make the relevant changes in the SDN controller forwarding tables, and push those forwarding tables to the underneath switches. The switches, you can say, while they are high performance switches because they're implementing the data plane, from an intelligence standpoint, what are they? They're more dumb switches. They're not too intelligent. The intelligence completely lies in the control layer. Okay, so these switches will just follow what the control layer is saying, and the control layer is deciding what it has to say based on the requirements of the application layer. So I've actually crafted a more programmable network, a more software controlled network, and therefore the term software defined networking. I can define how the network behaves via software based control. Okay, so I can now in these data planes continue to have implementations which are still hardware driven. But the forwarding table which gets configured in the switch using the ASIC, let's say I have an ASIC over here, which does some packet forwarding. It consults the forwarding table to make that forwarding decision. The forwarding table is what is the configurable part. And that makes it more software defined or programmable in nature. Okay. So I'll introduce this new concept now called generalized forwarding, which follows the ideology of match plus action. So let me just explain, take a moment to explain what do we mean by generalized forwarding and why. What we discussed earlier in the internet, the way we said traffic forwarding happens in the data plane in the internet, why that is becomes a special case of generalized forwarding. So what actually happens in the internet is also called destination based forwarding. Why? Because what did we say every router in the local function in the data plane of every router is doing? When an incoming packet comes in, I look at the destination IP address in the packet header. I look at the destination IP address and then I use that destination IP address to match it in the forwarding table. And then based on what the forwarding table tells me, I forward the traffic on an outgoing interface towards this destination. So because I'm making use of the destination address to decide what way I should forward this traffic, this approach is also called destination-based forwarding. That's what we do in the internet. But now I will introduce you to a concept called generalized forwarding, which can be very easily implemented using an ideology called match plus action. So let's carefully try to understand what it is. And I must thank Jyoti for continuing to post some messages on the chat, which should be useful for everybody. I mean, the posts always talk about some of the things that we are discussing. So thank you, Jyoti, for that. Okay, so generalized forwarding, what do we mean by generalized forwarding? Generalized means that, so we've already said that every router contains a forwarding table. That still remains true. Right? Every router has to have a forwarding table in the data plane. The forwarding table is what gives me the information on how to forward the traffic. So in reality, what we are implementing as part of the forwarding function, which we said is the local function in the data plane, is nothing but a match plus action abstraction. What do we mean by match plus action? The packet comes in, I match certain bits of the arriving packet. In the case of the internet, we were matching the destination IP address. We were looking for the destination IP address in the forwarding table. Wherever it matched, we took an action based on what the forwarding table told me. It told me that I have to forward it over a particular interface. I did that. So destination-based forwarding that I was doing in the internet was actually nothing but the match plus action abstraction. I match the IP address bits to the forwarding table columns. When I find a match, I take action based on the second column, which tells me forward it on to this outgoing interface. Okay. Now, while this was limited, this match action in the case of the internet was limited to just the destination IP address, and because of that reason, we called it destination-based forwarding. In general, if I generalize this whole thing, and by now people who've done this lab activity 1 have seen that in reality, the headers that go along any data through the network, they have a lot of fields and a lot of information being carried. So the data link layer we saw puts its own header, which has what? The MAC address, destination MAC address, source MAC address, type of layer 2 protocol. So it has a lot of information in the layer 2 header. Similarly, the network layer puts its own layer 3 header, which has the destination IP address, source IP address, next the layer protocol, whether TCP or UDP, the checksum, the TTL, all these are fields in the LC header. Similarly, the transport layer we saw in the last class, UDP and TCP, put in their own transport layer header, which has source port number, destination port number. TCP has a whole lot of fields. So if I can generalize the forwarding approach by saying that not only can you match on the destination IP address, but a router has the flexibility to look at multiple header fields in L2, L3, L4 headers. And based on that, define the action to be taken for the packet. And now we are saying that this action need not just be forward on a particular interface. There can be other actions possible, like drop the packet. If certain fields of the packet header match, drop it. That could be one action. Copy the packet and duplicate it to two interfaces. So I'm duplicating one packet incoming, two packets outgoing. The same packet getting duplicated and sent to two different directions. Modify the packet. Certain fields in the packet could get changed. Simply log the packet, which means I want to maintain an audit trail of what traffic was flowing in the network. Certain packets I just want to log. Multiple actions that are possible. So if I can do this, what I've implemented using the same match plus action abstraction is a more generalized forwarding approach. Okay. So when we look at the flow table now, so when we earlier drew the flow table in the network layer data plane, we were saying it has destination IP address in column 1 and outgoing interface in column 2. And this is what was helping us implement destination-based forwarding. I match the destination IP address which bits in these rows. Wherever it matches, I pick the outgoing interface and forward. But now we are saying the forwarding table, don't just think of it like a forwarding table. Think of it like a flow table. What do we mean by a flow? A sequence of packets having a similar characteristic. Right? By characteristic, I mean they probably have the same fields in some of their layer 2, layer 3, layer 4 packet headers. They all belong to the same type, same flow. Okay? So let's say I am sending traffic from my laptop to Amazon web server. It's a flow of traffic because not only will the IP addresses be same in every packet, the MAC addresses, the quality of service, all of them will be the same. So I can call it a flow. A flow of traffic going from one machine to another machine. So think of the forwarding table as a flow table. And the columns in the flow table as the left hand side telling what fields are you required to match in the packet headers. And right hand side tells you what action you have to take on that packet. So I'm saying flow is defined by the header field values, and you can use as many header field values to determine a flow. You can say, okay, traffic which comes into a particular link, in from a particular link, with a particular set of network IP addresses, with a specific TCP field, let's say source port number 25, sorry, destination port number 25, source port number 110. They belong to one traffic flow. So I basically said that these values in different packet headers, they define a flow. So if I can handle a flow in a particular manner, I am basically implementing a very generalized forwarding approach, which allows me to treat every flow of traffic differently. Okay. So in generalized forwarding, I am implementing a very simple packet handling rule, which, as I said, on the left side has a set of matching rules, which tell me these are the fields to be matched in the packet header. If they all match, then what does it mean? It means it belongs to a particular flow. Because all those packet values in the packet header fields, they are matching what I've defined in the flow table. So I can characterize it as a particular flow. Now, based on how I want that flow's traffic to be handled, I define the action. So I can say drop this traffic belonging to this flow, forward it onto this outgoing interface, modify the traffic like this, or duplicate it and send it one packet out of the outgoing interface, one packet to the controller, SDN controller as well. All these actions I can define. So there are other things I can do, including defining priority. If there are multiple patterns matching that I'm trying to do, if something matches more than one, then what rule has a priority? I can define counters. So if a flow matches a set of rules, then I can also say in the action, count how many bytes of traffic have gone through the router for this particular traffic flow. Count how many packets have gone through the router or the data plane of the router for this specific packet flow, traffic flow. Okay? So I can do a whole lot of things. Once I've identified a traffic flow, I can do a lot of things for that traffic flow. Okay? This is called generalized forwarding, and this is what SDN implements as a general match plus action behavior. So I'm on the right, you will see some example of what kind of flow table entries you can have. The first entry tells you source equal to star dot star dot star dot star means any source IP address, but destination towards 3 dot 4 dot star dot star. So what does it match to? It defines a traffic flow that is going towards a destination network where the nodes have an IP address starting with 3.4 and anything after that. So it's a subnet. Any traffic going towards this subnet, I've classified it as a flow of traffic. And what am I telling the router? I'm saying, okay, if this is the traffic type, forward it on to outgoing interface 2. So this essentially becomes nothing but your traditional destination-based forwarding that we follow in the internet. So as I said earlier, destination-based forwarding becomes a special case of generalized forwarding. But what else can I do? I can say, okay, if there's traffic specifically coming from this subnetwork, this particular subnetwork, 1.2 star dot star, and going anywhere in the internet, star dot star dot star dot star is the destination. Drop this traffic. Why do I want to do that? Maybe I've already identified that the subnetwork, which has IP address 1.2 star dot star, it belongs to a malicious entity. They are spamming the internet with malicious traffic. Or let's say a lot of spam emails are getting generated from this network. I'm sure you are familiar with this concept also, right? So as a user, you would have seen, I mean, this is something which is implemented in the internet. There are functions which are implemented which discover the source networks for spam emails, and they actually disable those networks. So this could be a rule to do that. If 1.2 star dot star is a network generating on spam emails, I want it to be disconnected from the internet. So I put in a rule which says any traffic generated from this network, drop it. Okay. So that is one flow table entry. I can have a flow table entry which actually calls out a particular source. I want to monitor what kind of traffic this machine is generating. It is, let's say, more for implementing legal interception. So a law enforcement agency has asked the network operator that I suspect this machine generating lot of, let's say, illegal traffic. Let's say a lot of child pornographic material is being generated and pushed on the internet from this machine. We want to legally intercept the traffic and see what is happening. What can I do? I can set a flow rule saying if any traffic comes with this source address and goes to any destination, don't care about the destination, forward that traffic to the SDN controller so that it can log it and store it for legal interception purposes. Anything that you can think about as a network application is possible to do with just flow table rules. Hence, if I go back a few slides to this architecture, now probably it's easier to understand why we are calling it software-defined networking. One of the network applications could be legal interception. I want to implement legal interception. So if the if from a GUI interface to this application, I can say, okay, this is the source IP address which I want to intercept. This network application using the REST API will send that requirement to the SDN controller. SDN controller will create that kind of a forwarding flow table rule, send it via OpenFlow to the switch routers, right? Push it to all the routers in the network. So any router which gets that traffic will send it to the SDN controller. The SDN controller will log it or maybe forward it to this legal interception application. So any networking application can be implemented and controlled via software. That is the beauty of software-defined network. And underneath, the technology which enables it is the concept of generalized forwarding or the concept of flow tables. Okay, so this is what, in a nutshell, SDN is all about. So this slide is just telling you that what are the fields in the packet header on which I can define the match action. Okay, Gautam has a question. Sir, apart from IP address, can I have any other type? Exactly the question I was about to answer, Gautam. So what all fields in the packet header can I define the matching pattern on? All that you see underneath. I can do it on the layer 4, which is the transport layer header, like the TCP source port, UDP source port, TCP destination port, UDP destination port. I can do it on the layer 3 header, IP type of service. This is the quality of service. IP protocol. This basically says TCP or UDP or none. IP destination address, IP source address. You can do it on the layer 2 header. Source MAC address, destination MAC address, Ethernet type, VLAN ID, VLAN priority. So what is VLAN? We will cover in a while, slightly later when I talk about network virtualization. So I can do it on the layer 2 header fields. I can even do it for the physical layer. So this is transport layer, this is network layer, this is data link layer. For the physical layer, it's what is the incoming port on which the traffic was received, ingress port. I can use that to define a match action. So matching action can be defined on all of these fields. See, once the matching pattern can be defined on all of these fields. Once the patterns matches, I can define a whole set of actions. Forward packet to a particular port, drop a packet, modify certain fields in the header, encapsulate the packet in another packet header and forward it to the controller for legal interception and also. So yes, this gives a lot more flexibility. Where was that comment? I missed it. I didn't get it. Now, okay, it just came in. Okay, I was looking above. Yeah, so it gives a lot more flexibility compared to your traditional destination-based forwarding that's implemented in the internet routers. Okay. This is what OpenFlow is all about. Okay. So alongside, the third thing I mentioned is you can maintain certain statistics as well. If pattern has matched, you can take an action, and you can also make certain counters, increment certain counters like packet counters, byte counters, which match this action. Okay. So this is what OpenFlow allows you to do. So certain examples of OpenFlow. This is destination-based forwarding. So what have I done? I've taken all these fields from here on the subsequent slide. Okay. And I'm saying, what is it that I'm matching out of all these fields? Star means anything. So here I'm matching a particular IP destination address, and the action I'm saying is forward on port 6. This is what? Destination-based forwarding that I do in the internet. So it means all IP datagrams going towards 51.6.0.8 should be forwarded to output port 6 of the router. What if I have to implement a firewall? I can do something like this. So the requirement that the application, so this is the requirements coming from the application layer. The application layer gives me a requirement saying block all traffic destined towards TCP port 22. Who uses TCP port 22? SSH, secure shell. Right? Secure shell uses port 22, destination port 22. So I don't want to support any SSH traffic in my network. What do? I want to block it. I set this kind of a flow table rule. Don't care about any of the other fields, but if the destination port for the TCP matches 22, action drop. So I've implemented a firewall function in the router itself. Okay, another case of implementing the firewall. The application layer tells me I want to block all traffic being sent by a particular node, 128.119.1.1. This is the flow table rule I'll create. It will block all traffic generated from a source. Why? Maybe that source hasn't paid certain, I mean, it's not paid the monthly fee for the internet service provider for, let's say, last 6 months, or he's the source of spam email generation. I want to block our traffic. So this, I can do this. I can even implement layer 2 forwarding. So remember where we had talked about this. Within a local area network, what had we said? We had said that I could implement layer 2 switching. I can forward traffic based on MAC address. So what we saw on the previous slide was layer 3 destination based forwarding. What we do in the internet. Within a local area network, I can do layer 2 based forwarding. So what do I say in that case? If this is the destination MAC address, then forward the traffic on port 3. So any switch can look at this rule and do, we call this not routing, we call this switching, because it was packet forwarding at layer 2. So it can switch the traffic based on destination MAC addresses within a local area network. I can do layer 2 destination forwarding. So anything that you can think of is possible to do with flow table rules, and that's what SDN allows you. So the abstraction that OpenFlow provides is the match plus action abstraction, and this is actually what the OpenFlow protocol is all about. The OpenFlow protocol, which is the southbound protocol between the SDN controller and the SDN switches. SDN switches. This is the OpenFlow protocol. So the OpenFlow protocol actually allows you the method to populate these flow tables. Define the match plus action. So if I have to implement a router, I use match, longest destination IP prefix, action, forward on a switch. If to have to implement layer 2 switching, I do match on destination MAC address, action, forward, or broadcast, flood. If I have to implement a firewall, I say match the IP addresses and TCP UDP port numbers, action, permit, or deny. If I have to implement network address translation, people who understand what network address translation is, for those who don't, ignore it. See? I'll say match a particular IP address and port number, and the action is rewrite the IP address and port number with a different IP address and port number. Generally, network address translation, when you go from inside a private network to the outside to the public network, you translate from a private IP address to a public IP address. So the rewriting is rewrite the private IP with a public IP. So this can be a NAT functionality can be implemented as a flow table. Okay. So this slide, I will give it to you for you to look at later. It shows how an SDN controller sitting in a network can create a network-wide behavior for forwarding traffic by setting flow tables, not just in one switch, but in multiple switches. So in this network, you see there are 5 hosts, host 1, host 2, these are endpoints, host 3, host 4, host 5, end systems. They are connected to 3 switches, switch 1, switch 2, and switch 3. Those that forms your network. These are all SDN switches. So an OpenFlow controller controls these switches. Now I have a requirement which says datagram from host H5 and host H6 should be sent to host H3 or host H4 via switches S1, then to switch S2, and then to the destination. So what have I done? I have defined a complete flow of traffic. I want the traffic from H5 or H6 destined towards H3 or H4 must go via S1 and then to S2 and then to the destination. This is my requirement. How do I fulfill this requirement? By the SDN controller creating flow tables for each of these switches accordingly. Okay? So that they follow this rule. So source address 10.3.star.star or 10.2.star.star, which signifies host H3 or H4. The switch 3 will forward it on interface 3. So it will go to S1. S1 has rules which tell it to forward to port 4. Traffic will go here. It reaches S2. S2 has rules which define traffic for H3 to go here, H4 to go here. So I have created what? A network wide behavior of how my traffic should flow through the network via a central SDN controller. So SDN allows me to create such network-wide behaviors. It allows me to centrally control how traffic should flow through the network, passing through what intermediate switches or routers. All of it I can control from a central entity based on the application's requirement. Okay. So in summary, we are introducing what we call as generalized forwarding, which is nothing but a match plus action. In a way, what it provides me is a form of network programmability. So what I lost when I moved the data plane functions into the hardware was programmability in the network. What I gained back by bringing in SDN was once again this ability to be able to control network-wide behaviors using a software-driven interface. So I've regained the network programmability in my networks. Okay, why do I need SDN in data center networks? Why does this network programmability help me? I'll defer that discussion slightly to the later part of today's class. Okay, but this completes our discussion on SDN, and we are actually slightly past the 1 hour boundary. So I can give you a 4 minute break. It's 11:36. Take a 4 minute break till 11:40 and come back and we'll start network virtualization and network function virtualization. Okay, it's 11:37. So come back by 11:41. Okay, 4 minutes. We'll start at 11:41. Okay, I think it's 5 minutes. We have sufficient break, so let's start. So while this part of the course is titled Network Function Virtualization, we will actually be covering two parts. We will first talk about the concept of network virtualization. What do we mean by network virtualization or virtualized networks? Right? Because this will be very useful for us when we get to cloud network. So we'll first talk about network virtualization in general, and then we will talk about the specific aspect of network virtualization, which is network function virtualization. Okay. So very quickly, what is the virtualization concept? Everybody knows, right? You've been exposed to it in cloud computing. Yes, no? Virtualization in general is the idea that you take a piece of physical hardware, implement what in generalized way we call it as the virtualization layer, and create multiple instances of that resource in isolation so that you can run multiple virtual instances over a physical instance. That's the general idea of virtualization. Now, very commonly, we are used to see what we call as compute virtualization. That's the most common form of virtualization that all of us are exposed to. I have four physical machines. And the reason I have four physical machines is because each of them is running a different operating system. So I needed four machines. But then I saw that each of them was hardly being utilized, 25%, 15%, 22%, 15%. So what I did was I took a single piece of physical hardware machine, ran the virtualization layer. That gave me multiple what we know as virtual machines, VMs. Each of them is isolated from each other. So in each virtual machine, I could run the guest operating system of my choice, and then on that operating system, run the required applications and achieve a higher utilization of 75% for my single machine. So it helped me optimize the cost of keeping a machine or running a machine by better utilization of my hardware resources. That's what compute virtualization is. Now, the same concept, while it's very easy to appreciate it in the concept, in the context of a compute machine, the concept also similarly exists in storage, and it also exists in networks. Okay, so if you look at any data center, okay, any data center, you will see that the resources that a data center has are characterized into three types. You have compute resources, which are the server machines. You have storage resources, which are the storage devices like your RAID disks and so on, tape drives, everything. And you have the network resources. Okay? Now, virtualization is something that is possible on top of each of them. When I do it over compute, I get what we know as virtual machine. This is something each one of us is very familiar with. When I virtualize a piece of storage hardware, what do I get? I get multiple virtual disks or storage areas. Right? This also, I believe, you should be fairly exposed to, or at least in cloud computing, maybe you've been exposed right now to things like elastic block storage and so on that AWS provides, which are nothing but virtual storage. You've taken a physical disk and created isolated storage spaces for different people in it. So these are virtual storage. But what do I mean by a virtual network? How does virtualization work in the concept of a network is what we are going to focus first on by talking in general about network virtualization. Okay, so what is network virtualization? Network virtualization is the process of combining hardware and software network resources and network functionality into a single software-based administrative entity called your virtual network. Now, this might seem to be a very confusing definition. So rather than trying to remember the definition or going through it, let us rather try to understand it more conceptually. Okay, what do we mean by a virtual? Or rather, let's look at a diagram to just try to understand it with a picture. What do I mean by a virtual network? So let's say I have, just like I had a physical server machine or a physical piece of storage, I have a physical network. Okay. I have an entire physical network which has its own infrastructure. What is the infrastructure in a physical network? Switches and routers. Okay. And of course, communication links. All of them connected together in a particular fashion create a network topology. Okay. So what I get is a physical network connected in a particular topology. That is what I'm calling as my physical network infrastructure. Now, if I have a way to implement a virtualization layer on top of this physical network infrastructure, what is that virtualization layer? We'll talk about it. How do I implement virtualization? We'll talk about it. But what can I get? I can get multiple virtual networks created on top of an underlying physical network, which can be same way, just like I treat virtual storage as being isolated from each other. A VM being isolated from another VM, even though it's running on the same physical machine. By isolation, I mean it can independently function. They don't have any direct interaction. They're isolated from each other. I can similarly have multiple isolated virtual networks on top of a single underlying physical network. Okay. Why do I need this kind of a technique? Why would I need multiple virtual networks on top of a single underneath physical network? One of the classic and very old examples. So network virtualization is not new, by the way. It has existed for as many years as networks have existed. But the oldest example of network virtualization is virtual LANs. How many people have heard of the term virtual LAN? Okay, Gautam, you are also right. VPN is also another example of a virtual network. I'll come to that as well. But VLANs have existed even before VPNs. Okay. Tanya has a question. So, sir, does that mean it will reduce traffic and help in scalability? Okay, more than reducing traffic, Tanya, it's distribution of traffic across isolated instances of the virtual network. Okay, so rather than having all traffic flowing over a single physical network, and actually the traffic is still going to flow over the physical network, but I isolate the traffic belonging to one entity from that of another entity by saying or separating it into two different virtual networks. Okay, so we'll try to understand that with one of the oldest examples of network virtualization, which is VLANs, virtual LANs. So what is virtual LAN? Okay, let's first understand what we call a LAN, local area network. Local area network is a network that is predominantly within an autonomous system, and where switching is used as the primary function for traffic forwarding. So let's say this is my BITS Pilani institutional local area network. Right? Local area network. So what do I see in the BITS Pilani local area network? Well, there are so many departments. Let's say computer science is one department, triple E is another department, and each of them are hosted in their own blocks or buildings. So each of them will have their own faculty devices networked together using some topology. Let's say this is how the computer science block looks like. There are two switches. The square ones are switches. That's the diagrammatic notation we followed till now. So square blocks are these switches, layer 2 switches, which connect the faculty desktop machines together. Similarly, in the triple E department, I have one switch which connects the triple E department nodes together. And maybe there's another sub-block or another floor in that department which has other faculty machines, and they are connected via another switch. Now, how do these people together talk to each other? Maybe there's another next level hierarchical switch which connects all of them together. So this creates my local area network within BITS. Okay. But sometimes I have to go outside of the bits network towards the internet. So what do I need? This circular notation is what we've used for a layer 3 router. This router helps me connect to the external internet using IP traffic. Okay, so that's how I do. Now, normally a local area network is considered what? It's considered a single broadcast domain. What do we mean by broadcast? It means that any layer 2 traffic, there are a lot of traffic in the layer 2 network, in a local area network, that is typically broadcast in the entire network. Okay? One of the protocols which is known to broadcast traffic in a local area network is address resolution protocol, R. What is R? It's a protocol where if some traffic comes from outside the internet for a particular destination IP address. So let's say traffic is coming for an IP address a.b.c.d from the internet. This router, layer 3 router, receives that traffic. Now inside, this is a layer 2 switching domain. So I'm forwarding traffic based on MAC addresses, not based on IP addresses. But what I've received from the internet is traffic based to a particular destination IP address. What does this router do? It broadcasts a request in the layer 2 network. This is called an ARP request, saying I have received some packet from the internet for a destination machine which has an IP address of a.b.c.d. Whichever machine has this IP address, respond back to me, giving me your destination MAC address. So this is broadcast traffic. It gets broadcasted in the entire layer 2 network. It's called an ARP request. Every machine in the network will get it. Whoever has this IP address, let's say this machine over here is a.b.c.d. It will see one-on-one respond back to the router saying, it is my IP address and my MAC address is M:N:O::P::Q::R. This is my MAC address. So now what will this router do? It will create a layer 2 frame with destination MAC address as this and send that layer 2 frame, which will get layer 2 switched through the network because it's a layer 2 network towards the destination. That's how traffic from outside the internet is switched within the local area network. And before I can do that, I need the MAC address of the destination machine. So I use ARP as a protocol, address resolution protocol, to get the MAC address corresponding to the IP address. And this results in some broadcast traffic, which gets broadcasted in the entire layer 2 network. Similarly, there are other known protocols in a local area network like DHCP, Dynamic Host Configuration Protocol, which also broadcast a lot of traffic in the layer 2 network. If you don't know a MAC address, where is it? Right? So I have some traffic for a MAC address. Let's say this machine, okay, with the source MAC address of M::N::O::P::Q::R wants to send a packet to a destination MAC address A::B::C::D::E::F. This is what it has to send. But it doesn't know where is A, B, C, D, E, F. Where is it, this node? None of the switches know. The switching table has no entry for it. What happens? The traffic for an unknown MAC address gets broadcast everywhere in the network. Whichever machine has this MAC address will pick it up, all others will discard it. So there is, in a local area network, a lot of broadcast traffic. Okay? And hence a local area network is actually called a broadcast domain. Now, what would happen if the local area network grows in size? I have new departments coming up in Pilani: mechanical engineering, chemical engineering, civil engineering. More blocks getting set up, more such machines getting. The local area network scale is going to grow. That's one problem. So the amount of broadcast traffic is going to grow a lot more than what it exists when there were just two departments. That's one problem. Two, with interdisciplinary programs coming in, computer science faculty will often have meetings in the EEE department. EEE faculty will often go to mechanical engineering department to talk about mechatronics programs, mechanical plus electronics. So faculty move. Let's also say that new faculty are joining and the computer science department, the building is already full. There is no space for a new faculty, but Triple E says, I have a seat. So computer science faculty is forced to sit in the Triple E building. So what is happening? The network is growing and people are sitting across buildings. And also broadcast traffic is also growing. So what do I have? I have administrative issues. There's too much of broadcast traffic. Users are moving across buildings. So I can't avoid broadcast because if a computer science guy moves from computer science block to Triple E block, I can't limit the broadcast traffic to just the computer science building because otherwise this guy who sits in the Triple E building will lose the traffic. So to solve the broadcast challenge, but also to create logical sub-networks within the local area network, we use a concept called virtual LANs. So I say so my need is to limit the broadcast traffic. Traffic which should just be between the computer science faculty should just be broadcast between them. It should not go to Triple E, mechanical, and so on, and vice versa. That will help me reduce broadcast traffic. So what I do is I create a red colored virtual LAN. I call it the computer science department VLAN. I create a blue colored virtual LAN. I call it a Triple E department VLAN. So any traffic which is supposed to be only between Triple E people should just be limited to that VLAN. Anything which is just meant for computer science people should just stay within that VLAN. And of course, anything that is meant for everybody should be broadcast to everyone. So what am I doing? I'm reducing the scope of the broadcast. Right? However, when I do that, this challenge comes in, which I said earlier. A CS user moves to the Triple E department and he sits there. This guy has moved and he got a seat over there in the Triple E building. How will he receive computer science broadcast? He can still continue to receive it if I extend the red virtual LAN to also the Triple E building. So the building is nothing but a physical entity. And the infrastructure in that building is nothing but, no, Jyoti, it's not even inter-VLAN routing. I've just extended the computer science VLAN to another part of the physical network. It's still the red VLAN. Look at the diagram. The red VLAN has gotten extended to the Triple E building. But it's still the red VLAN. It's still the computer science VLAN. So what are we saying? We are saying VLAN is a virtual concept. It's a logical concept. It has no dependence on the physical way the physical network is created. I can have a physical network in a particular fashion. Computer science building has a particular topology of the physical network. Triple E building has a particular topology of the physical network. But at the virtual level, I can create a red VLAN that consists of all these red nodes. I can create a blue VLAN which consists of everything else minus this node. Okay. This is what we mean by a virtual LAN or a VLAN. And this concept has been there for years or decades. So how do I do it? What we see on the previous figure, this particular switch, focus on this. What is this switch catering to? It is catering to two types of VLANs, a blue VLAN, because there are 1, 2, 3, 4 devices connected to this switch which belong to the blue VLAN. But there is one device connected to the same switch which belongs to the red VLAN. I'm using blue and red to basically denote the computer science and Triple E VLAN. So what will this switch look like? This switch actually will look like every switch has multiple ports, incoming ports. Think of them as colored ports. So I can say some of my ports are red colored. Some of the other ports are blue colored. The blue colored ports belong to the computer science VLAN. The red colored ports belong to the Triple E VLAN. Any machine which is part of the red VLAN, I'll connect it to red colored ports. These are virtual colors. In reality, you don't have coloring on those ports. Any computer science machine, the computer science faculty who moved from CS department building to EEE department building, will go there and connect to a port that belongs to the CS VLAN. In a way, this switch can be virtually seen. While it's a single physical switch, it operates as multiple virtual switches. It's like having a red switch and a blue switch bundled into one single physical switch. But both these are two independent switches, and think of each of these switches as one broadcast domain. So traffic which is meant for blue VLAN will remain within this part of the network only, this part of the network. Any traffic which is broadcast within the red VLAN will stay within here only. So anything which is generally broadcast will go on all ports. Okay, so as local area networks scale, my broadcast traffic creates a lot of overhead. Not all traffic has to be globally broadcasted. Some traffic can be locally broadcasted within sub-departments of the local area network. And that I can achieve by creating what we call as virtual local area networks. By the way, this way of creating virtual local area networks is also called port-based VLANs, because I'm segregating ports of a switch to different VLANs. This is called port-based VLANs. There are other ways to create VLANs, but we'll not get into it. Okay, port-based VLANs is the simplest way to do it. Okay. So port-based VLANs enable the special type of switches which support VLAN as a technology. It's a concept, and they provide what we call as traffic isolation. So traffic from port 1 to 8 gets broadcasted only within this domain. Traffic for between these ports gets broadcasted only here. So it's providing isolation of traffic. But anything which is globally transmitted or broadcasted can still be sent via a third. So think of it that like two different LANs. One red LAN, one blue LAN. And if I have to send traffic between this machine and this machine, what can I do? Just like I send traffic between two LANs, I send it via a router. Traffic from one LAN to another LAN goes via a router using IP addresses, layer 3 forwarding. And typically, because these switches have all of it integrated, layer 2 switching as well as layer 3 switching, sometimes some people use the term layer 3 switch to indicate a switch which also has the routing functionality inbuilt, so that it can route traffic across VLANs as well. So forwarding between the VLANs is typically done using IP routing, and the switch typically also has a layer 3 routing function inbuilt, which allows it to send traffic across the two different VLANs. Another thing to understand is that while we took in the earlier diagram a simple example of a single switch whose ports got split into two different VLANs, it's possible to have something more complicated than that. You can have a network where there were two switches. Okay, if I take you back to that original diagram, we had multiple switches, switch 1, switch 2, switch 3. Let's say some EEE guy also moves here, connects to switch 1. What will happen? Both switch 1 and switch 3 have some red colored ports and some blue colored ports. So you'll find some situation like this. Let's call this switch S1, this S3. So there are some EEE folks connected to S1, some connected to S3. Similarly, some computer science folks connected to switch S1, some connected to S3. So all I'm saying is VLANs could be spanning multiple switches. Okay? Underneath, there's a physical network, but the virtual network could be spanning multiple physical switches. So what do I need? In this case, such switches also support a special port called a trunk port. Because red color traffic has to be broadcast between these ports, but also has to be sent between these ports. So any traffic generating from a red colored port has to be sent via the trunk port to the switch S3 and then broadcast among these red colored ports as well. Similarly, a blue traffic generated from here will obviously get broadcasted on the blue ports, but it also reaches the trunk port, which forwards it to the trunk port of the other switch, and then it gets broadcasted on the blue ports of the other switch. So essentially, in the trunk port, I can carry what we call as VLAN tagged traffic. This traffic has to have a tag which says whether this traffic is for VLAN equal to red, or whether the traffic going over the trunk port is for VLAN equal to blue. Accordingly, the neighboring switch will forward it on the right colored ports. Okay? So VLAN is a so how is VLAN implemented? So when we have the look at the layer 2 header, layer 2 header has a earlier layer 2 header had a destination MAC address and a source MAC address. Now the layer 2 header has an additional field called VLAN ID. So this VLAN ID is basically identifying the red or the blue or the black or any other virtual network. So there's a new field in the layer 2 header called the VLAN ID. It carries the ID of the virtual network. And based on this ID, I broadcast the traffic only through those colored ports which belong to that VLAN, to that ID. So in a way, by identifying different virtual networks by different IDs and assigning these ports to one of those IDs, I have created multiple virtual networks. Okay, I'm going back multiple slides now. Yeah. So what have I done? I've created multiple networks. This is VLAN ID 1. This is VLAN ID 2. This is VLAN ID 3. Underneath, they are using the same physical switches, but these switches have some ports which belong to VLAN 1, some to belonging to VLAN 2, some belonging to VLAN 3. Every port has that. Some ports belonging to VLAN 1, some ports belonging to VLAN 2, some belonging to VLAN 3. So essentially, using our underlying physical infrastructure, I have created multiple virtual networks on top. And they have their own broadcast domain. Each of them is a local broadcast domain. Each of them is a virtual network, isolated virtual network in its own sense. Okay. So what is the virtualization layer in this example? The virtualization layer is very simple. It's a field called the VLAN ID in the layer 2 packet header. By just having a field like this, I've implemented the virtualization layer. Okay, simplest example of network virtualization. Okay? So this type of network virtualization, where we create many parts of a physical network into multiple virtual networks. It's called external network virtualization. Why? Because I'm taking a physical network and crafting multiple virtual networks out of it. I'm creating multiple subparts of that network as multiple virtual networks. Yeah, Tanya, you're right. Trunk port is like a highway. It connects two cities. The two cities are the two switches. Within those two switches, you can say there are two municipal regions, the red region and the blue region. So the trunk port connects the two cities, which have individual multiple municipal regions within them. Okay. So this form of virtualization is called external network virtualization. Okay. Let's take another example of external network virtualization, which Gautam said a while back. Oh, sorry, was it Gautam? Yeah, Gautam said a while back. VPNs, virtual private networks. Okay. So when we look at external network virtualization, you can do it at multiple layers of the protocol stack. You can do it at the physical layer, but it's seldomly done. Nobody does. You don't craft and virtualize networks at the physical layer, but it can be done. I mean, if you think of it, you'll find some ways to do it, but seldomly done. Nobody implements it. Layer 2, it is done. The example we just looked at, VLANs. It is done by adding some tags in the MAC frame. Sorry, the tags we just saw was the VLAN ID. And that's what provides us virtualization. At layer 3, network layer, the example of an external virtual network is a VPN, a virtual private network. I am sure there will be nobody in this class who has never used a virtual private network. Is that right? If somebody has never used a VPN, say, sir, I haven't. Let me know. But I'm assuming everybody has used a VPN. What is a VPN? You are creating a layer 3 virtual network. How? So you have the internet, which is a physical network. This is your enterprise network. In the enterprise network, you have a server. Right? This is the server. And this is your organizational or enterprise network. Okay? So whatever organization you belong to, it's your organization network, and there's a server. Typically, you are sitting in your office with a desktop machine, and over the enterprise network, you connect to this server. But what happens when you are at home and you have to do work from home? Your laptop machine is at your home. You are connected to the internet, which is a physical network. You are connected to the internet, of course, via the ISP and so on. I'm not going to draw the internet topology. It's the ISP and then the regional ISP and then the tier 1 ISP, whatever. But your enterprise network is also connected via the internet. So physically, you are always connected to that enterprise server, physically. But practically, the enterprise doesn't allow anybody on the public internet to access this server for security reasons. Because this server is supposed to be accessible only over what we call as a private network. The enterprise network is a private network, right? That is also one of the reasons why we are using private IP addresses within it. Okay? You don't want to use public IP addresses, they are scarce. So it's a private network. Anybody inside the network can access this server. It's a private network, but anybody outside this network from the public domain cannot access this server. It's an enterprise private server. Now, when I'm at home and I need to access this server, what is required? It's required that this private network be extended to my laptop also over the physical network, which is this internet. So I'm creating what we call as a virtual private network. I'm extending the enterprise private network right up to my home and including my laptop also into the private network. But I'm doing this over the physical network, which is the internet. And how do I do that? I use some tunneling techniques. To create a tunnel, secure traffic, I create a secure tunnel from my home right up to the enterprise using technologies like IPsec, IP security. I create a secure tunnel between my laptop and the rest of the enterprise network. So in a way, I've extended the private network right to my home to include my laptop, not all the devices in my home, but just my laptop by creating that tunnel to my laptop. And while it's going over an underlying physical network like the internet, nobody can interpret or see this traffic because it's a secure tunnel. Okay, so this is another example of a virtual network created on top of a physical network, which is the internet. A lot of layer 3 applications, sorry, layer 4 and above applications create some kind of an overlay network. Many P2P applications use a virtual network to communicate amongst them. Think of a Bitcoin network or a file sharing network like BitTorrent, which is a file sharing network over the internet. It's an example of a virtual network created between point-to-point network created between machines in a virtual net form. So virtual networks can be crafted or created at every layer using different virtualization techniques. Here we use a tunneling technique in layer 3. Here we use a VLAN tag. Using different virtualization techniques, we can create virtual networks at various layers of the protocol stack. See? This, by the way, as I said, is called external network virtualization. You have a physical network, on top of it, multiple virtual networks are being created. Another term that exists in the case of network virtualization is internal network virtualization. By internal network virtualization, we mean that you have a single machine, like a laptop. But because you have multiple VMs that have been created on top of it, due to compute virtualization, so you have compute virtualization in a laptop. So you have multiple VMs, VM1, VM2, VM3, and so on. Now, what if I want to create some sort of a network between these virtual machines as if they were physical machines? So if I drew them as separate machines, VM1, VM2, VM3, and I wanted that they be connected like this, that there is a switch, which is a layer 2 switch, and they should be connected like this to each other. Then what am I doing? I'm creating a network between these VMs. In reality, this compute virtualization that sits in your laptop, it is what? It is a hypervisor. Everybody knows what a hypervisor is? If somebody doesn't know, say no on the chat. Otherwise, I'll assume everybody knows what a hypervisor is. So the compute virtualization is done by a hypervisor. The hypervisor in reality also has a virtual switch, which we call a vSwitch. It's a software implementation of a switching function. Okay, so now you remember from STN that anything that I can do in hardware, I can even do in software. Okay, it's only because of speed that I go to hardware, but I can implement layer 2 switching in software. All I have to do is to look up a forwarding table, which can be kind of implemented as an array data structure, table lookup, and forward traffic. I can implement a switch in software. We call it a virtual switch. Okay? So the hypervisor has a switch, which we call as a virtual switch. It's a software implementation of a switch. And it connects these VMs together via this vSwitch. Okay? So this becomes the physical network inside a laptop. But what if I later say I also want to create on top of this physical network a virtual network such that VM1 and VM2 belong to one virtual network, whereas VM3 is a separate network in itself. If I use so just like I do external network virtualization, I'm trying to do it internal within a laptop as well. Creating virtual network between VMs sitting inside a laptop. This is what we call as internal network virtualization. Okay? Providing network-like functionality to containers or VMs within a single system. Okay, so this is what we mean by network virtualization, and I just gave you a few examples of how network virtualization has existed for a very long time using VLANs and VPNs, virtual private network. Yeah, these are some slides on internal network virtualization. I just drew it separately. So I showed you that you can have a virtual switch. The virtual switch connects to a physical network interface card. This is if you have to send some traffic out of the network. Every VM has a virtual network interface card. This is a vNIC. Just like you have a physical NIC, every VM has a virtual NIC, which can help it to connect to a virtual switch. The virtual switch is like a physical Ethernet switch, but it's a software implementation of the physical switch. Okay, so yeah, so that's what we mean by network virtualization. Okay? Now coming to network function virtualization. How is network function virtualization different? It's a completely or a slightly different concept where we are saying that it is not the network that we are virtualizing, but we are virtualizing the network functions. So what are these network functions? When we discussed SDN, we said there can be different kind of network functions. Routing is a network function. Switching is a network function. Firewall can be seen as a network function. A NAT gateway can be seen as a network function. A load balancer, network load balancer specifically, can be seen as a network function. Now, historically, we've always associated these network functions with physical hardware, routing with routers, switching with switches, firewalls with firewall nodes, firewall devices, NAT gateways with once again gateway nodes. We've associated them with physical devices because that's how historically they were. Routers were a piece of hardware plus software where the entire function of routing was implemented. And Cisco used to be the biggest provider of these routers. Juniper used to provide these routers. Similarly with switches, firewalls, Palo Alto would have its own firewall. Right? So you would have combination of hardware software entities which used to be called these network functions. But as we learned a while ago, all of these network functions can be implemented in software. Right? So when I implement the same network functions, I untie them. Right? The term I'm using is untie. I untie them from the underlying hardware. I implement these network functions in software. And I say that actually they can run on any common off-the-shelf COTS hardware. This is what we mean by network function virtualization. Okay, so I'll actually try to explain it using diagrams, but and then I'll come back to this slide. What is the benefit? Yeah, extracted from software is also fine. Okay, so if I look at the traditional approach to networking, every network function was a piece of hardware. This is how you would see it in figure. Firewall would be shown something like this. Network address translation gateway, session border controller, a special type of BGP router, border controller router, a mobile network node called the GGSN or the SGSN, a DSL network aggregator node called the BRAS, something like this, a deep packet inspection firewall, something like this. So what was it? Every network function was shown as a specific hardware and software. And there used to be one physical hardware implementing one network function, so one node per role. That was the traditional networking approach. What is the modern approach? The modern approach is think of everything like a virtual appliance implemented in software. It's the same deep packet inspection firewall, the same DSL aggregation node BRAS, the same mobile network GGSN, SGSN, but they are in software. Okay? And I can run those pieces of software which I'm calling virtual appliances. So these are called network appliances. That's the term used, network appliances. They are like your home appliances, but used for the network. So we call them network appliances. Here we are calling them virtual appliances. And we say that these are software. So they can run on any common off-the-shelf server machines. So in a data center, if I have these rack servers, which are standard high volume servers, I can run these virtual appliances on the rack server machines. And this is the network function virtualization approach. It's also called the virtual appliance approach. So I want to create a router, run a router in a data center. What I do is I take a software implementation of the router. I put it on one VM of a high volume server and it runs as a virtualized router. We call it a V router. Similarly, I want to run a switch. I take a software implementation of a switch, run it on a VM, which is a virtual machine on a standard high volume server in the data center. What do I get? I get a virtual switch, a software implementation of the switch. This is the NFV concept, network function virtualization concept. Okay, so the migration is from the classical network appliance-based approach, where one network function runs on one piece of hardware, to a network virtualization approach, where in a data center you have the standard high volume server storage available already, and you have independent software vendors who are providing all these network functions as virtual appliances. You just buy them off a marketplace, just like you buy an Android application off a Google Play Store. You buy a virtual appliance out of a marketplace, install it on a standard high volume server, and you say, voila, I have my router. I don't need to go to Cisco to buy a router. I purchase the router as a software application, a virtual appliance from a marketplace. I get a VM from AWS an EC2 machine. I install this software on the EC2 machine and I have my router. Why do I need Cisco? Okay, I'm not saying likes of Cisco and all are going to go out of business. They have migrated towards this whole new architecture of building the solutions for the NFVs and data center environment. And not everything is data center. You still have the internet, right? So not, as I said, SD and NFV are more concepts that are applicable in local administrative networks and data center networks. But this is a different approach to networking called the network function virtualization approach. Sorry, Jyoti, I don't get the question. How do you ensure security in NFV? I'll actually ask you a question. How do you ensure security in a classical network appliance approach? It's still the same piece of software. It's running on a dedicated hardware. Now we are saying you take a piece of software and run it on a shared piece of hardware. So if from a security standpoint, you're saying, how do I make sure that other pieces of software running on the same shared hardware do not exploit this piece of software? Then that is where cloud security comes in. How do you make sure that one VM is secure and it doesn't have to be a physical compute machine, a dedicated compute machine? I can run a VM and it can be as secure as a dedicated compute machine. That's where the cloud security topics come in. Okay, so we'll not get into that. I mean, that's the other course I teach, and I'm teaching this semester, cloud security. How do you achieve security between functions running on a common piece of hardware on the cloud platform? That's a separate ball game altogether. I'll not get into that. We are just talking networking. Okay, so I'll excuse me if I don't answer that question because it'll just open a Pandora's box. Okay, so Yuvraj has a point which is very valid. The speed provided by actual physical devices was the advantage. How does software-based appliances work in this regard? Very valid point, Yuvraj. So the advantage of network function virtualization. See, why is this stuck on this slide? Give me a moment. Okay, I know we are towards the end of the class. Once again, I'll just need 10 extra minutes today. We'll complete this. And then we'll be able to complete the mid-sem course actually. So you'll get a couple of weeks for revision then. You don't have to, I mean, next week class will be there. It actually will be a very interesting class next week because it will be the introductory class for data center networking. Oops, it's just stuck. I think this guy knows that the class is over. Well, give me a moment. Yeah, now it comes. Okay, let me go back a few slides to this slide to answer that question which Yuvraj asked. Okay, so network function virtualization has a lot of advantages, but it has its own disadvantage as well. One of the biggest advantage of network function virtualization is it provides an opportunity for pure software vendors. Earlier, the entire world was dominated by the likes of Cisco's and Junipers and so on, who basically built custom hardware, proprietary hardware to run specialized functions like routing. Yes, Yuvraj, that did give us the benefit of that proprietary hardware plus software combination gave me the advantage of speed. Cisco would optimize its hardware, have certain functions running on ASIC, some on network processors in such a fashion that I get the maximum speed out of it. So that traditional network appliance approach gave me speed and performance. But what it meant was there was no role for software companies and vendors to provide any solution. NFV opens up the doorway to these pure software players to build networking solutions as virtual appliances. It creates a new approach to creating virtual networks in a data center network by using, so remember what I talked about, internal network virtualization. So in the internet where I have physical machines, I can connect them via physical switches to create a physical network. But what do I have in a data center network or in a cloud environment? I don't have physical machine. What do I have? I have VMs, virtual machines. Now, are all virtual machines in the same physical hardware server? No. Some VMs may be in some physical hardware server and some VMs may be in some other physical server. But what if I want to create a virtual network between these VMs? These are virtual machines and I want to create a virtual network between them. So machines running within the same physical hardware server will need something called the internal network virtualization to connect to each other. That's what we just covered. So what will I need? I need a vSwitch. That's what NFV enables for me. But a VM in some other physical server, let's say this is a physical hardware server, this vSwitch will connect to a physical NIC card. That physical net card will connect me to the physical network. Sorry. Camera got on somehow, I don't know why. I clicked on some wrong icon. This is always right. Yeah. Okay, I lost that diagram. It is. Right. And that physical network will then take me to the other physical server where there's another physical NIC card. And then from there, it will go to a virtual switch in the hypervisor and then to this VM. So using a combination of physical switches and virtual switches, I can create a virtual network between VMs. So it opens a new innovative way of creating virtual networks in a data set. Now, while these are the advantages of NFV, the disadvantage, as Yuvraj pointed out, is we are losing performance. The virtual router or a virtual switch will definitely not have the same performance as a traditional router or a traditional switch which is running on custom built hardware to improve performance. Okay, but can I still do something about it? That is one of the topics we will cover when we come to network performance in the context of data center network. This is the topic we will cover. How do we improve the performance of NFV virtual appliances? That's a topic we will cover in one of the classes later after mid-sem. Okay, so Yuvraj, your point is valid. That is one of the disadvantages, but we live with that disadvantage because it gives us a lot more other flexibilities. Okay? And we try to overcome that disadvantage using certain performance enhancement techniques, which I will cover in a later class after mid-sem. Okay, so this is the maximum I'll answer for now and refrain the rest of it for later. Okay, so now that we've understood SDN independently and NFV, let's compare between them. We've seen that they are two independent technologies. One can exist without the other. NFV is a redefinition of the network equipment architecture. And it leads to the birth of a new kind of service provider who's a software vendor creating network functions, virtual appliances. So it's a redefinition of the network equipment architecture. Whereas when you look at SDN, it's a redefinition of the network architecture. I'm moving the control plane to a central entity, creating a new network node. It's a new network architecture. Okay, so the two are independent and distinct from each other. Yet we often, okay, I am skipping some slides because they're not too relevant. We don't need them. So I'm just skipping them. They'll be there in the deck if you want to see, but not too important. This slide is, for example, just giving you the NFV architecture. I can quickly go through it. And this is actually, in a way, I've already gone through it. See, this is what I said was your data center infrastructure. What do you have in a data center? You have compute, you have storage, you have network. So it's the physical hardware resources. What do you run on top? You run a virtualization layer. The virtualization layer is different for different components. It's the hypervisor for the compute. It's a different layer for the storage. We saw network virtualization can be done using different techniques, having a VLAN ID at layer 2 or having a tunnel at layer 3. There are different ways in which you can create a virtualization layer on it. So what does it give you in the data center? It gives you virtual resources. It gives you a VM, virtual compute, virtual storage, virtual network. This is what we call as the NFV infrastructure. So this is the hardware and physical infrastructure of a data center. This is the NFV infrastructure. Now, this virtualized infrastructure that I have, I can share it between multiple tenants like you and me who go to AWS and we create our own VM, our own virtual storage, our own virtual network on AWS. What are we using? We are using this NFV infrastructure. So when we use this NFV infrastructure, we want our virtual compute, our virtual storage to be connected via our own virtual network. How does that happen? It happens via using virtual network functions, routers, gateways. We use, so by now, if in cloud computing, you've already spawned your own VPC, virtual private cloud on the AWS. If you've done that experiment, you know that you spawn your own virtual machine, you get your own EBS storage, multiple virtual machines you can connect via your own routers. What are those routers? They're actually software routers, VNFs. So you are creating in AWS your own logical abstraction of a network. And this is what NFV enables you to do. Okay. This is why I'm saying this is a building block. NFV is a building block for cloud networks. Okay. We'll keep talking about it more and more as we move ahead. Now, while SDN and NFV are independent technologies, in the data center, we often use the term SDN/NFV because the two technologies are often used in tandem. When I say they are used in tandem, the figure gives you a very good example of what I mean by tandem. Think of two tenants using the same data center network to host their infrastructure, create their virtual cloud network. One tenant has the red traffic, the other tenant has a blue traffic. Okay. Now, the traffic obviously goes to the internet as well and comes to and fro from the internet. But then it also passes through VMs and machines within the data center as well. So what is NFV enabling in the data center? NFV enables you to create these virtual appliances, firewalls, antiviruses, video optimizers, parent controls. All of these are virtualized network functions. By the way, previous diagram, there were two terms, NFV and VNF. Okay. NFV is the technology, network function virtualization. VNF is the term that I use for a virtualized network function. So like we said, vRouter, virtualized router. Router was the network function. vSwitch. Switch is the network function. So we generalize it and we call it a VNF, virtual network function. So all of these firewalls, antivirus, video optimizers, parental control, I can implement them as virtual network functions and host them on a high capacity server in the data center. For every tenant, based on their need, I can create, spawn on the fly these VNFs. And then it's not just about spawning virtual network functions. What can I do for these tenants? I can route their traffic using SDN flow tables. Think of these VNFs as SDN enabled virtual network functions. Think of them as open flow compliant virtual network functions, which means they can receive open flow messages in the form of flow tables. What can SDN do? It can control as a central controller all of these virtual network functions and craft the flow tables to create what? We used a term, create a network-wide behavior, create a programmable network. And I can do this separately for different tenants for their different flows. The blue is one traffic flow. The red is another traffic flow. It could belong to one tenant to another tenant. I can use SDN to create the network-wide behavior for red flow. I can use SDN to create a network-wide behavior for the blue flow using the VNF appliances. So SDN and NFV can be used in tandem together in a data center to create this kind of a networking experience for your tenants. On and underneath NFV platform. What was the NFV platform? Virtual compute, virtual storage, virtual network. This is the basis of a cloud network. This is the basis of cloud computing. Okay. This is how networks work in the context of cloud computing. Okay. So today we got an overview to what SDN and NFV is. From next class, we will start the topic of data center networks. Try to understand how these differ from internet, or how the traffic pattern differs, and then get deeper into how does data center networking work, and how are virtual cloud networks, tenant-specific virtual networks created over a data center. That's something we start from next class. Okay, so now to answer a few administrative questions, we will still have the class next week, okay, where we will have, actually, as I said, it's going to be a very interesting class next week. So I want everybody to join. We'll introduce data center network and talk about some very interesting topics of data center network. Okay. Yes, Arup, I had earlier communicated that we'll start it after EC2 because I had no hope of completing the mid-sem syllabus until class 8. But because of the extra class that we had and you all cooperated for that class, we have been able to meet it. So we are back on track with our handout. Okay. So now I still have class number 8, which as per handout is our introductory class for data center networking, and we are back on track. Okay. So next class will be on data center networks. It will not be part of your mid-sim course syllabus. Okay. So just join that class for learning. Don't be worried that that will also come in mid-sem exam. It will not. The mid-sem syllabus is till today, till SDN and NFV. Okay, so till today, class number 7 is your mid-sem course. You have 2 weeks to prepare for your mid-sem. The next class we will have, it will be an interesting class on introductory topics on data center networking. So please join, even if it is not part of your ECT syllabus. Third thing, final thing. Monday, I will enable quiz 1. Okay, and quiz 1 has the same syllabus as your mid-sem exam. So that will force you to do an early revision of all topics for your mid-sem. It will actually help you because you'll be prepared upfront. So I'll open quiz 1 on Monday. I'll give you slightly more than a week time to take that quiz. So whenever you feel you are ready with all the syllabus, take that quiz. It will once again be till the ST and NFV topic. It's a 15-minute quiz, right? So you can, I'm sure you can find out 15 minutes in this week-long time that I'll give you to take that quiz. Whenever you think you are prepared, take the quiz. Okay. The syllabus, as Yuvraj asked, for regular and makeup is the same. Okay? So it will be the same until SD and NFB, the same syllabus for the regular exam, the same for the makeup exam. Okay. So yeah, Tanya, I know some people are giving the regular, some are giving the makeup because you can't give all exams together. So yes, I know most students do that. They distribute the courses subjects across regular and makeup. So that's fine. I mean, I don't have a say in that. It's up to you. But the syllabus is the same for both regular and makeup exam. Okay, guidelines for Samanvita I'll give next time. We still have one more class. So what will come in EC2, I've already clarified until today's class. Guidelines on EC2 I'll cover next class. Right? We are already above time, 15 minutes above time. Let me not take more time for the class. Next time we'll have a class and we will, no, classes will not get cancelled. We will have class 8 next week. Okay, we will have the next class. And then there is the mid-sem. Like, okay, complexity, Yuvraj, is the same for regular and makeup. Same syllabus, same complexity. Okay. So thank you, everyone. Thank you for staying another 15 minutes to help me complete the course. I mean, essentially, we took 1 extra class and 2 extra 15 minutes, and we are back on track to how the handout wants us. So that's a good thing. Okay. Even with all the extra time we took in all these classes, we are back on track. So thank you for joining. Thank you for giving me extra time. And next time we'll start what the handout says for contact session 8. Thank you. Bye-bye.